Dear students, welcome to a new video for the sampling subjects. Here we will begin with the estimation of the standard errors from a sample. The formulas for the standard errors of the estimated population mean and the total used primarily for three purposes. Number one is to compare the precision obtained by the random sampling with that given by other methods of sampling. Number two is to estimate the size of the sample needed in a survey that is being planned. Finally, to estimate the precisions actually attained in a survey that has been completed. The formulas involve S capital square, which is the variance. They mean the population variance. In practice, this will not be known, but it can be estimated for a sample data. The relevant result is stated in the theorem 2.4. Theorem 2.4. For a simple random sample, the variance equal to x small square equal to summation of yi minus y power all square over n minus 1 is an unbiased estimate of s capital equal to summation yi minus y capital power square over n minus 1. We can prove that by the following steps. First, we put s square equal to 1 over n minus 1 summation yi minus y power small minus y power capital all square. Then we can take summation for the first brackets, which is summation yi minus y capital power all square minus n y small power minus capital Y power square. Now, the average of overall simple random samples of size n by the arguments of symmetry used in the theorem 2.2 is the expectation of the summation for yi minus capital Y power all square from I equal to 1 up to small n is equal to n over n of n over capital N for the summation of from I equal to 1 up to capital N yi minus y power all square, which is equal to small n times capital N minus 1 over capital N multiplied by s capital square. By the definition of s square, furthermore, the theorem 2.2, the expectation of n small multiplied by y power minus capital Y power all square is equal to capital N minus n over capital N times s square. Hence, the expected value for s small square is equal to capital S square over n minus n multiplied by capital N, which multiplied all by the two brackets n times capital N minus 1 minus capital N minus small n. Here we can eliminate all these together to get the value that expected value for s small square equal to s capital square. This means that there is an unbiased estimate for the s square. Now we will get a corollary, which is unbiased estimates of the variances of y small power and y hat equal to ny power, where variance for y power small equal to s square was for small y power, which is equal to capital S square over small n times n capital minus n small over n, which is equal to 1 minus f. Again, for the y hat, we can substitute in the previous theorem to get s square for y hat equal to n square s square over n times n capital minus n small over capital N, which is equal to n square capital N times s square over n times 1 minus f. For the standard error, we will take the square root, so the rule will be s for y small power equal to s over root n times root 1 minus f. And for the total population, y hat equal to capital N times s over root n times root 1 minus f. These estimates are slightly biased. For most applications, the bias is unimportant. The reader should note that the symbols employed for the true and estimated variances of the estimates. Thus, for y bar, we write the true variance V for y small bar, which is equal to sigma square y bar. The estimated variance is V small for y bar, so the equal to s square for small y bar. Now we will take a look for the confidence limits. It's usually assumed that the estimates y small per and y hat are normally distributed about the corresponding population values. The reasons for the assumption and its limitations are considered in section 2.15. If the assumption holds, lowering the upper confidence limits for the population mean and total are as follows. For mean, y par hat for the lower equal to small y par minus ts over root n times root 1 minus f, and capital Y par hat for the upper limit equal to small y par plus ts over root n multiplied by root 1 minus f. And for the total population mean, the y hat for L equal to capital N times y bar small minus t and s over root n times 1 minus f, and y hat u equal to ny par plus t and s over root n times 1 minus f. The simple t is the value of the normal deviates corresponding to desired confidence probability. The most common values are in the confidence probability 5%, if we have 50 equal to 0.67, 80%, 1.28, 90%, 1.64, 95%, 1.96. Finally, 99% equal to 2.58. If the sample size is less than 50, the percentage points may be taken from the student's table with n-1 degree of freedom. These begin the degrees of the freedom in the estimated variances s square. The t distribution holds exactly on if the observations y small I are themselves normally distributed and n capital is infinite. Moderate departure from normality don't affect it greatly. For small samples with very square distribution, special methods are needed. Let's take an example. Signatures of a petition were collected on 676 sheets. Each sheet had enough space for 42 signatures, but on many sheets a smaller number of signatures had been collected. The numbers of signatures by sheet were connected on a random sample of 50 sheets, about 7% of samples. With the result shown in the table 2.2, estimate the total number of signatures to the petitions and the 80% confidence limits. Let's see the solution for this example. The sampling unit is a sheet, and the observations yi are the numbers of the signatures per sheet. Since about half of the sheets had the maximum number of signatures, 42, the data are presented as a frequency distribution. Note that the original distribution appears to be far from normal. The greatest frequency began at the upper end. Nevertheless, there is a reason to believe that experience that has the mean of samples of 50 are approximately normally distributed. So we find that small n equal to the summation for fi equal to 50, small y equal to summation for fi times yi, which is equal to 1471, and summation for yi fi square equal to 54,497. Hence, the estimated total number of signatures is y hat equal to capital N times y small par, which is equal to 19,888. For the sample variance small s, we can substitute in the rule for s squared and get the values equal to 1 over n minus 1, which is 1 over 49 times 54,497 minus 1,471 square over 50, which is all equal to 229. From 2.22, the 80% confidence limits will be 2 sides if we have 19,888 plus or minus t small times capital N times 1 minus root 1 minus f over root n, which is equal to 18,107 for the lower limit and 21,669 for the upper limit with 80% limits. A complete count showed that in the table here. Thank you for listening to this video, and we will join in another video.